When you get your weekly allowance, you can either spend all those $20 that very same day or collect it over several weeks and spend it on something of more value. The more money you save, the more likely you can get that bicycle you've always wanted. This is one of the dilemmas we go through. We can't have it both ways. This concept is similar to how knowledge about the velocity and position of objects can simultaneously be known. This is the Heisenberg's Uncertainty Principle from quantum mechanics. This inequality basically sums up the relationship between the position and momentum of an object. Delta certifies that we are oblivious of both the position and the momentum. H, the Planck's constant, is a small figure. All we need to know is that both the position and momentum is greater than 0. The more precisely you know the position, the less precisely you know of the momentum, and vice versa. Let's take an example. When your friend group passes through a narrow door where only one can pass at a time, since we know the precise location you went through, your positions are guaranteed. But once you pass the door, you can move in any direction, changing your momentum. Likewise, when you pass through a wide door together, your positions are scattered, thus uncertain. But since you're walking together, there is more certainty of your momentum as your direction doesn't change as easily. Knowing that objects behave like a wave and a particle at the same time, let's apply this to the real world. When we record the probability of finding an object on a graph for a wave and a particle, for the particle it's only found in one particular position, while velocity is unspecified, whereas in a continuous wave, position is largely unknown. However, considering that wavelength is related to momentum, we are assured that a car driving at 100 km an hour or a massive whale swimming slowly correlates to short wavelengths. Therefore, we can conclude that large momentums creates a short wavelength, and vice versa. However, here's where the problem arises. We know a particle's position, but not its momentum, and we know a wave's momentum, but not its position. Accordingly, we can deduce that when we have a pure wave, we are certain of its momentum as its wavelength is constant, but subsequently, it decreases the area of likelihood of the object's presence. When creating a wave by adding different wavelengths, we have a higher probability of position, but since we have too many wavelengths collectively, we lose certainty of momentum. This is the Heisenberg's Uncertainty Principle. The more accurately we know of one of these values, the less accurately we know of the other. Precisely speaking, when it comes to subatomic particles, it becomes virtually impossible to measure any property without meddling with it in some way. Thus, uncertainty is inevitable, no matter how cautious we are when we're measuring, even though accuracy doesn't play a part. It is rather that one cannot know all properties about the particle at the same time, as there is an indispensable limit to what one can know about the quantum system. So next time when you receive your allowance, remember, you can't have the best of both worlds.